idea behind ultra-wideband (UWB) communication is that spreading data across many frequencies requires less power to reach the same distance. The key characteristics of UWB are that UWB uses wide spectrum of frequencies and consumes very low power. It has a short distance, 2 to 10 meters. However, signal permeates obstacles such as walls and has a data rate of 110 at 10 meters and up to 500 megabits per second at 2 meters. Ultra-wideband technology is loosely defined as any wireless transmission scheme that occupies a bandwidth of more than 25% of a center frequency or more than 1.5 gigahertz. One of the promising application areas is in medicine. Ultra-wideband is a communication method used in wireless networking that uses low power consumption to achieve high bandwidth connections. In other words, it's meant to transmit a lot of data over a short distance without using too much power. Originally designed for commercial radar systems, UWB technology has had applications in consumer electronics and wireless personal area networks. IEEE unable to resolve disputes and form a single standard. After some initial successes in the mid-2000s, interest in UWB declined considerably in favor of Wi-Fi and a 60 GHz wireless network protocol. Ultra-wideband wireless radios send short signal pulses over a broad spectrum. This means that data is transmitted over a number of frequency channels at once, anything over 500 megahertz. For example, a UWB signal centered at 5 GHz typically extends across 4 GHz and 6 GHz. The wide signal allows the UWB to commonly support high wireless data rates of 480 megabits per second up to 1.6 gigabits per second at distances up to a few meters. At longer distances, UWB data rates drop considerably. When compared to the spectrum, the spread spectrum, ultraband's broad spectrum use means that it does not interfere with other transmissions in the same frequency band, like narrowband and carrier wave transmissions. Some uses for ultra-wideband technology in consumer networks include wireless USB, wireless high-definition video, wireless printing, wireless monitors, next-generation Bluetooth, peer-to-peer connections, file transfers without a PC. Zigbee is named after a technique that honeybees use to communicate new-found food sources to other members of the colony, referred to as the Zigbee principle. The Zigbee standard 802.15.4 arose from a desire to standardize wireless remote control technology, especially for industrial equipment. Because remote control units only send short commands, they do not require high data rates. The chief characteristics of Zigbee are 1. It is a wireless standard for remote control, not data. The target use is industry as well as home automation. And finally, there are 3 frequency bands used: 868 MHz, 915 MHz, and 2.4 GHz, with data rate of 20, 40, or 250 kilobits per second, depending on the frequency band. Zigbee has very low power consumption with 3 levels of security defined. Zigbee is well suited for a wide range of control uses in just about any market. The Alliance has focused its standards development efforts around the commercial, residential, energy, consumer, and industrial sectors. It has developed global standards for energy management and efficiency, home and building automation, healthcare and fitness, telecom, and consumer electronics. Here are just a few examples of what this wireless standard can control. Infrared technology is often used in remote controls and may be used as a cable replacement, such as for a wireless mouse, the Infrared Data Association, IRDA, has produced a set of standards that are widely accepted. The chief characteristics of the IRDA technology include a family of standards for various speeds and purposes for systems that have a range of 1 to several meters. The directional transmission covers a 30-degree cone with data rates between 2.4 kilobits per second and 16 megabits per second for data. The IRDA technology generally uses low power consumption, while there are some very low power versions available. The infrared signal may reflect from surfaces but cannot penetrate solid objects. Radio frequency identification, RFID technology, uses an interesting form of wireless communication to create a mechanism. A small tag contains identification information that a receiver can pull from the tag. Some features of RFID. There are over 140 RFID standards that exist for a variety of applications. Passive RFIDs draw power from the signal sent by the reader. Active RFIDs contain a battery which may last up to 10 years. There is limited distance, although active RFIDs extend farther than passive. They can use frequencies from less than 100 megahertz to 868 to 954 megahertz. They are used for inventory control, sensors, passports, and other applications. Radio frequency identification uses electromagnetic fields to automatically identify and track tags attached to objects. The tags contain electronically stored information. Passive tags collect energy from a nearby RFID reader's interrogating radio waves. Active tags have a local power source, such as a battery, and may operate hundreds of meters from the RFID reader. Unlike a barcode, the tags do not need to be within the line of sight of the reader, so it may be embedded into the tracked object. RFID is one method of automatic identification and data capture. RFID tags are used in many industries. For example, an RFID tag attached to an automobile during production can be used to track its progress through the assembly line. RFID tagged pharmaceuticals can be tracked through warehouses, and implanting RFID microchips in livestock and pets enables positive identification of animals. RFID tags can be attached to cash, clothing, and possessions, or implanted in animals and people. In 2008, the RFID industry was worth $11 billion. Of that, passive RFID tags make up $5.01 billion, and RFID readers make up $2.85 billion. Now let's move to another wide area networking technologies. Let's talk about cellular networks. Cellular systems were originally designed to provide voice services to mobile customers. The system was designed to interconnect cells to the public telephone system. Currently, cellular systems are being used to provide data services and connect to the internet. In terms of architecture, each cell contains a tower, which is generally a group of adjacent cells connected to a mobile switching center. The mobile switching center tracks a mobile user and manages handoff as the user passes from one cell to another. The figure illustrates how cells might be arranged along a highway. When moving between two cells belonging to the same mobile switching center, the switching center handles the change. When a user passes from one geographic region to another, two mobile switching centers are involved in the handoff. Wireless WAN technologies can be divided into two categories: cellular communication systems and satellite communication systems. So a user moves between two cells belonging to the same mobile switching center. The switching center handles the change between the cells. When a user passes from one geographic region to the mobile switching center, from the two regions are involved in this handoff. Perfect cellular coverage occurs if each cell is a hexagon because the cells can be arranged in a honeycomb. In particular, cellular coverage is imperfect in practice. Most cell towers use omnidirectional antennas, omni means all, that transmit in a circular pattern. Obstructions and electrical interference can attenuate a signal or cause an irregular pattern. In some cases, cells overlap, and in others, gaps exist with no coverage. The figure illustrates the ideal and realistic coverage. Additionally, the variability or inconsistency of cell density is possible. In rural areas where the expected density of cell phones is low, the cell size is large, and often a single tower is adequate for a large area, compared to an urban setting where there may be many cell phones in a given area. For example, consider a city block in a large metropolitan area. In addition to pedestrians and people riding in vehicles, the area can contain office or apartment buildings with many occupants. These regions must be able to support the higher usage, so a practical deployment uses various size cells, with smaller cells used to cover metropolitan areas. Because cell clusters are not arranged in a perfect honeycomb, and cells typically overlap, cellular communication must follow a key principle. Interference can be minimized if an adjacent pair of cells do not use the same frequency. To implement the principle, cellular planners employ a cluster approach where a small pattern of cells is replicated. The figure illustrates clusters of 3, 4, 7, and 12 that are commonly used. In geometric terms, each of the shapes in the figure can be used to tile a plane. That is, by replicating the same shape, it is possible to cover an entire area without leaving any gaps. If each cell in a given shape is assigned a unique frequency, the repeated pattern will not assign the same frequency to any pair of adjacent cells. The figure illustrates a replication of the 7-cell cluster, with a letter in each cell to denote the frequency assigned to the cell. Each letter corresponds to a particular frequency, and each cell within a cluster is assigned a frequency. When the cluster pattern is replicated, no adjacent cells share a common frequency. Telecommunications industry divides cellular technologies into generations that are labeled 1G, 2G, 3G, 4G, and 5G, with intermediate versions labeled 2.5G and 3.5G. 1G began in the late 1970s and extended through the 1980s, originally called cellular mobile radio telephones that used analog signals to carry voice. 2G and 2.5G began in the early 1990s. The main distinction between 1G and 2G arises because 2G uses digital signals to carry voice. The label 2.5G is used for systems that extend a 2G system to include some 3G features. 1G is analog, no SMS, no mobile data or browsing. 2G and 2.5G are digital. 3G and 3.5G began in the 2000s and focused on the addition of higher speed data services. A 3G system offers download rates of 400 kilobits per second to 2 megabits per second and is intended to support applications such as web browsing and photo sharing. 3G allows a single telephone to roam across the world. 4G began around 2008. It focuses on support for real-time multimedia such as television program or high-speed video. They include multiple connection technologies such as Wi-Fi and satellite. Anytime the phone automatically chooses the best connection technology that is available. 3G was designed to use voice telephone standards inherited from the old analog phone system. 4G was designed to use IP standards as the foundation for all communication. In practice, many cellular providers still send voice calls over 3G systems and only use 4G protocols for data. LTE stands for long-term evolution. 3G and 3.5G higher speed data services exist. 4G IP phone automatically chooses the best connection technology available. What does 5G mean? Simply put, 5G is short for fifth generation. You may see the standard called 5G NR. The NR stands for New Radio. When 4G long-term evolution mobile networks started rolling out nearly a decade ago, consumers welcomed the new era of rich media mobile browsing, representing both an evolution of the 4G standard and a revolution in radio technology. 5G technology promises to transform the 2020s into a time of unprecedented connectivity and technological advancement. With higher capacity and speed, plus ultra-low latency, 5G will power innovation that would have been impossible under the 4G LTE standard. All four previous generations of mobile networks use macro cell towers, hundreds of feet tall, requiring vast power outlays to transmit over long distances. 5G works a bit differently. This upgraded mobile network uses a combination of frequencies from multiple bands to maximize the output. In addition to traditional macro cell towers, 5G will also use a large number of much smaller microcells for new millimeter wave spectrum bands to create a blanket of ultra-high speed network coverage. 5G is based on OFDM, which remember stands for orthogonal frequency division multiplexing, a method of modulating a digital signal across several different channels to reduce interference. 5G brings wider bandwidth by expanding the usage of spectrum resources from SU 3 GHz used in 4G to 100 GHz and higher. 5G can operate in both low bands, 6 GHz, as well as 24 GHz and up, which will bring extreme capacity, multi-gigabits per second, and ultra-low latency. 5G is designed to not only deliver fast, better mobile broadband services compared to 4G LTE, but can also expand into new service areas such as mission-critical communications and connecting the massive IoT. The next generation of mobile networks defines the following requirements that a 5G standard should fulfill. Data rates of tens of megabits per second for tens of thousands of users, data rates of 100 megabits per second for metropolitan areas, 1 gigabit per second simultaneously to many workers on the same floor, several hundreds of thousands of simultaneous connections for wireless sensors, spectral efficiency significantly enhanced compared to 4G, coverage is improved, signaling efficiency is enhanced, latency is reduced significantly compared to LTE. Fifth generation mobile networks or fifth generation wireless systems, abbreviated 5G, are the proposed next telecommunications standards beyond the current 4T IMT advanced standards, operating in the millimeter wave bands 28, 30, and 60 gigahertz. 5G planning aims at a higher capacity than current 4G, allowing a higher density of mobile broadband users and supporting device-to-device, more reliable, and massive machine communications. 5G research and development also aims to lower latency than 4G equipment and lower battery consumption for better implementation of the Internet of Things. There is currently no standard for 5G.